When is your test? Is it Tuesday?
Wednesday.
Okay.
I'm probably gonna see if I can meet with you on Tuesday night too.
Okay.
All right, cool.
All right. So they want the domain and range. Be careful to account for asymptotes and vertices. Okay. Not quite sure what they mean, but let's look at this. How do we get the domain out of this?
I don't know you.
Okay, the domain is the allowable values for x. We can talk about it algebraically, and then let's talk about it graphically.
Okay.
What determines what? Because we have a radical. If I said this to you, what can x be for this expression? Can x be anything, or is it restricted? Can it be negative?
No.
Can it be 0?
No.
Yeah, it actually can be 0. So it has to be greater than or equal to 0. That's what that means. So if I have this expression, in order to solve this, I set whatever's inside the radical greater than or equal to 0. Because that's what has to be true. And then I solve this inequality. What does this mean? X is what? Greater than or equal to 2. Okay? So that's all there is to the domain of that, is taking what's inside the radical, making it greater than or equal to 0, and solving for that inequality. Okay? The range is a little trickier. The range, you kind of have to think about it in 2 steps. The range is what y can be. And y has 2 parts. It has the part inside the radical, and it has the -5. What's the maximum that this can be? Trick question. Infinity. What is the minimum that this can be?
0. Oh, 2.
No, you're very correct. 0.
0.
Yeah, because if x is 2, that thing is equal to 0. So, but it can never be negative. So what is the lowest that y can be? If that part of it can at best be 0, the whole thing can be at best what? What's the lowest that the whole thing can be? Be -5. Since this part of it, since this part of it can be at best 0, then the lowest that the whole expression can be is -5. So that's the way we figure out the range. Now, let's graph this and make it far easier to figure out both, the domain and the range. First of all, I know the parent function, this being the parent function, graphs like this. So I can tell that this function is 2 units to the right and 5 units down. So if I go 2 units to the right and 5 units down and draw that same exact graph, now I read my domain off of my graph. I can tell, well, if it's all the allowable x values, it's got to be greater than or equal to 2.
Right.
And for the range, I can tell that the lowest it goes is -5, and it goes to infinity. There is no upper limit. That thing is not asymptotic to some line. In other words, as x goes to infinity, this whole expression goes to infinity. It does not have an upper bound on it. Okay? So there's a couple of ways to do these problems, and probably the best way to do them is algebraically. Because if you do them graphically, you've got to graph it, and that can take quite a bit of knowledge and problems. So let's look at 65. We've got y equal 1 over x plus 2 minus 3. What can x be? But more significantly, it's not so much what x can be as much as what x can't be. What can't x be? There's only one negative there's only one number that x cannot be. It can be negative infinity, it can be positive infinity. There's just one number that it cannot be. The denominator can't be 0, which means x plus 2 cannot equal 0, which means x cannot equal minus 2.
Okay.
Okay? And that's the way you solve those. Same way we solve the radical problems. If I told you that what's the domain of this, the answer is x squared minus x plus 2 has to be greater than or equal to 0, and then you solve that problem. So same thing with when you have fractions. If I said I have an expression that's 1 over x cubed minus 17, the answer is that x cubed minus 17 cannot be equal to 0. And then you solve that problem. So
the domain is really what x cannot be.
Kind of. So it's really the better way to look at it, although, like when I say this, what x can't be is negative. If I had logarithms, you've had logs, right?
Yeah.
What's the domain of that?
Zero? No. Yes.
No. X has to be greater.
10.
No. X has to be greater than 0. You can take the log of any positive number perfectly fine. You can't take the log of 0, and you definitely can't take the log of negative numbers. So the domain of log of x is actually more restricted than the domain of square root of x, because I can take the square root of 0. Okay. This just has to be greater than or equal to 0. This has to be greater than 0. So in general, domains are all about what x can't be. It's really a better way to look at it. Okay, so x can be all reals except x equal minus 2. Now, I'm not sure how your teacher wants you to express that. Do you use interval notation? Or does she let you say all reals except x not equal to 2?
I think he doesn't really care.
Let's make sure you know how to do interval notation for 65.
Yeah.
Interval notation will go, x could go from minus infinity up to minus 2, parentheses, because it can't be minus 2, combined with greater than minus 2 up to positive infinity. So that would be interval notation if they want you to express it like that. Okay, so that's domain. Now range, a little trickier. Again, range is always harder to figure out than domain. Domain is generally pretty easy. You just have to figure out what x can't be. But range, not so much. Let's talk about this number right here. or that expression. In fact, let's talk about this for starters. If I said y is equal to 1 over x, x can be anything except 0, right? So what would y be able to be?
Anything at all?
Good.
Oh, no, it couldn't. Yeah.
No, you're absolutely right. If I make x negative, no, not anything at all. There is one number that y cannot be.
Same thing as x, it couldn't be 0.
Can't be 0. X can't be 0, and y can never be 0, no matter what x is. But y can be anything else. You can make an x that would make y negative 10 trillion. And you can figure out an x that would make y positive 10 trillion. Or you can figure out an x that makes y 1 divided by a million. In other words, you can make y any other value except 0. So this range is anything except 0. Same thing with 1 over x plus 2. That's not really any different. I cannot make this 0 because it doesn't have 0 in the numerator. For you to make a fraction 0, the numerator has to be 0. But by manipulating x, I can make y anything I want except 0 in this part of the expression. In other words, if I make x be 2.1, I'm sorry, if I make x be negative 1.9, then this is equal to 10. If I make x be negative 1.99, this is equal to 100. So I can make y a billion if I want, and I can make y minus a billion. I just can't make it 0. So this part, we know what we can do with that. So when I add or subtract 3 to the expression, now what can y be and what can't it be? Remember that this I can make any number at all except 0.
Right. And so x could not be...
Not x,
0.
We're talking y.
Oh, y couldn't be 0 as well.
Well, actually it could once I've subtracted 3 from it. The left part of it cannot be 0.
Right.
So the whole thing cannot be what? If this part can't be 0, well, when I subtract 3 from something that can't be 0, then it can't be 3, minus 3. There's no way y could ever be minus 3. For it to be minus 3, then the 1 over x plus 2 part of it would have to be 0.
Right, okay. Oh, okay, so, like, to figure out what y could not be, you're literally taking, like, the x function out, or whatever, so in this case it would be the 1 over...
Yeah, you're separating it into 2 parts. The part that I have circled is one part of the function, and the other part that I have circled is the rest of it. And we can figure out that the left part can never be 0, so the combination can never be minus 3.
Okay, so you're really just, to find out what number cannot be y, you're looking at the second part of the function, the minus 3.
Exactly.
And that's pretty much the answer. And then
that's
for the
exactly
x, you take the first part.
The answer is the range is y is all reals except y cannot be minus 3. Because this is the only thing this can't be is 0. This can be any other number on the number line except 0, which means that minus 3 can be any number on the number line except the number that would result when this would be 0, which would be minus 3. But I think you get it, don't you?
Yeah.
Okay, let's move on. Be careful to account for asymptotes and vertices. Well, this last problem, where x could not be minus 2, because the domain was x can be anything except minus 2, if we were to graph that, that's a vertical asymptote. When x can't be a certain number, it means that that's a vertical asymptote. And then the minus 3 would be a shift, so we would have a horizontal asymptote there, and our graph would look something like that.
Okay.
And then you could read both the domain and the range off of the graph. But, like I said, that tends to be harder than easier. It doesn't help matters.
Yeah.
Okay, what can x be on 66?
X could be 0. No, cannot be 0.
Why not?
Well, the squared kind of throws me off.
You can square 0. There's nothing wrong with squaring 0. You can do most anything in mathematics. There's very, very few rules that you can't do. You can't divide by 0. You can't take the square root of a negative number, and you can't take the logarithm of anything but a positive number. And that's about it. There's not a whole lot of other rules that govern math. If you were trying to think up 10 commandments, you'd probably only come up with 3. Those 3 I just mentioned for math. The first one in everybody's list, go on the internet and ask for the 10 commandments of math, and you'll get 10 different lists, but every single one of them, the very first commandment is thou shalt not divide by 0. Okay? So x can be anything here. What can y be?
It could as well be anything.
Well, can it be negative?
Yes? No. No, it can't because x is being squared up.
Exactly. So y can only be positive or 0. And in fact, if you remember what the graph of this looks like, this one you remember, I'm sure, it's a parabola. That's y equal x squared. Notice that x goes from negative infinity to positive infinity, but y goes from 0 to positive infinity. So in this function, the graph actually helps quite a bit if you know what the graph looks like. $67. Domain?
Domain would be well, how do we do it because it's being multiplied by 2?
It's okay. Is there anything x can't be? Remember, domain is only about x.
No, it can't. It can be anything.
All reals. How about the range?
Oh, x can't be 0.
Sure it can. There's nothing that says you can't multiply a number by 0.
So it can be anything.
Yeah. You just can't divide by 0. Here, let me show you something. Take 10 and divide it by 1. What do you get?
10.
Now take 10 and divide it by 0.1. What do you get?
100.
Divide it by 0.01. What do you get?
1,000.
What do you get if you divide it by 0?
Nothing.
That's not correct. Division by zero does not produce. You put it in your calculator. That's what you get right there. What I was trying to show you is that as the denominator gets smaller and smaller and smaller, the result gets bigger and bigger and bigger. So when you get all the way to 0, your answer has to be infinity, which is not really a number. It's a concept. Any number divided by 0 is infinity. That's why you can't divide by 0. It's not because somebody arbitrarily made up a rule. It's because you don't get an answer. So here, x can be anything. You certainly multiply something by 0. What can y be? Is there anything that y can't be? When you're examining the range, like trying to figure out what y can be, start by, can it be negative? Yes. If I make x negative and make it some big negative, y is certainly going to be negative. Can it be positive? Yep. If I make x positive, y can be positive. Can it be any fractions? Yeah, I can make x be a certain type of fraction to make y be whatever fraction you want. Can it be 0?
Yeah.
Sure. If I make x minus 1/2, then this will become minus 1. Add 1 to it. We got 0. So y can be anything at all. No restrictions on 67. All right. Now we have something that is not...
For those, do I just put an infinity symbol?
Well, that's why I asked you how your teacher wants the domain given. There's lots of different ways you can state domain. Let me give you some examples. You could say x, all reals, x can equal all reals. That's the way you say negative infinity to infinity. Another way to state that would be negative infinity to positive infinity.
That's the way you use the negative infinity to positive infinity.
Then we should be
positive, negative,
that's called interval notation. And sometimes if we look at this function and you want to state the domain in interval notation, what would it be?
Positive infinity and positive
always start on the left.
So negative infinity.
To what?
To positive.
No, because it can't be 0. So we can't just say negative infinity to positive infinity except 0. The way we do that in interval notation is negative infinity to 0 combined, that's what that u means, with 0 to positive infinity. That's the same as all reals except x not equal to 0. In other words, these say the same thing. It's just that this is in words and this is interval notation. And interval notation is actually better because, well, it just is. It also allows you to, by using brackets instead of parentheses, it allows you to say, well, it can be 0, but it can't be between 0 and 1. So you might have a function that can be anything except from 0 to 1. It can't be that range. So maybe I would state it like that. So interval notation is the preferred mathematical way to state domain and range. Okay. So let's talk on 68. This is not an algebraic expression, in case you're wondering. We can't use algebra to solve this. This is an exponential expression. We usually solve exponential expressions using logarithms. But when we're talking about the domain, what can x be and what can it not be? Let's start with the easy part. It's the same part, actually. Is there anything x can't be? Can be negative infinity.
Yeah.
Can it be 0?
No.
Yes. 1.3 to the 0th power is equal to 1. And in fact, 2.3 to the 0th power is equal to 1. Negative 2.3 to the 0th power is equal to 1. In fact, 0 to the 0th power is equal to 1.
Why is that? That just anything to the power of 0 is equal to 1.
Yes. If you want to do an interesting experiment, go in your calculator, take 0.1 and raise it to the 0.1 power. You're going to get a very small number. No, I'm sorry, you're going to get what do you get? 0.1 raised to the
0.794.
Now go in and take 0.01 and raise it to the 0.01 power. What do you get?
0.954.
Notice what's happening. We're getting closer and closer to 1. Do this one and you'll get 0.99, I'll bet. So 0 to the 0th power really is 1. That just wasn't made up by some mathematician. It really is 1. Any number on the number line raised to the 0th power is equal to 1. So x can most definitely be 0. Can x be positive numbers? In this exponential function?
Yes.
So the domain must be negative infinity to positive infinity. Everything.
Positive infinity.
What's the range? Can y be negative?
No.
No, there is no value.
Yeah, it can.
No, it is. Tell me.
No, it can't. No.
Tell me a value for x that makes y negative.
None.
There aren't any. Even if I put in negative a billion for x, because all that means is 1 over 1.3 to the billionth power. That's not negative. That's a positive number. It's a very small number, but it's a positive number. So no matter what I let x equal, y has to be positive. Okay? Can y be 0?
Huh. Oh, okay.
Can y be 0? Can you?
Yeah.
Can you give me a value of x that makes y 0? There's none.
Okay.
So it can't.
So y has to be a positive number above 0.
Yeah. So it only is going to go from 0 to infinity. Or I could say y has to be greater than 0, not even equal to it. Or I could say all reals that are positive. Now, if this looks familiar to logarithms, it is. In other words, logs are the same thing as exponentials. I could express this logarithmically. And the fact that y has to be positive is the reason we cannot take logs of negative numbers. Or it's impossible to take the log of 0 because this part of the log, the argument, is y. It is the y from an exponential expression. That's why you cannot take logs of negative numbers or logs of 0.
Okay.
All right, here we have a polynomial divided by a polynomial. Now, what do we know about the domain? X can be pretty much anything except what? Except whatever makes that whole thing equal to 0. So to figure out what X cannot be, I have to solve this equation. How do I solve that?
Add 6 to each side.
No. This is a
Oh,
quadratic.
just square root it.
No, this is a quadratic. You got to factor it. Whenever you have a quadratic that has a number as part of it, the only way to solve it is to factor it or to use the quadratic formula. You don't want to use the quadratic formula if you can factor it. Factoring is much easier. So help me factor this. What goes
So
here?
it would be x and x.
Now do the signs. The signs is next.
It'd be minus and then plus.
Now step 3 is what?
Has to add to -6.
No, has to multiply to -6.
Multiply to -6 and then add to 1.
Good. So what factors do that? What factors of 6? When you say it has to multiply to 6, the better way to say it is factors of 6, because factors of 6 means two numbers that multiply to 6. Okay?
2 and 3.
There you go.
So it'd be x minus 1 times x plus 3.
Okay.
I mean, x minus 2 is what I meant.
Okay. Because you want to put the bigger of those factors with the positive sign because this is positive.
Right.
Okay. So, if I want to solve this for what x can't be, because if this thing is equal to 0, x can't be anything. So what values can x not be here? In other words, we're really solving.
X cannot be. X cannot be -2 or 3.
No. When you solve these, you set this is what can't be equal to 2, or equal to 0, which means x cannot be equal to 2. And x cannot be equal to -3.
Oh, okay.
Okay? In other words, you can't take it directly from this. You have to use the opposite sign of this. So whatever this number is, just make it the opposite.
Okay.
So what is the domain of this function?
Two and -3.
Well, let's do it in interval notation. Start on the far left. What can x be? Because interval notation tells you what x can be. In other words, you know that x can be anything except 2 or -3. So let's write that in interval notation, starting from the left side of the number line. Minus infinity to what?
Minus infinity
To what?
to infinity.
No, because you're jumping right through these two numbers that x can't be. You can't do that in interval notation. In interval notation, you have to go from one interval to the next interval to the next interval. In other words, you got to go from...
-infinity.
No, you go from negative infinity to negative 3.
Oh, and then 2 to positive infinity.
Well, hold on. I'm going to draw the number line here. Here's 0. Here's minus 3. Here's 2. X can be anything up to but not including that. And then X can be anything from there to there but not including that or that. And then X can be anything over there. So if I'm making that an interval notation, I'm going from negative infinity to negative 3 with a parentheses, combined with negative 3 to 2, parentheses, combined with 2 to positive infinity. You see that? You see why it's like that?
Yeah.
Okay. That's how interval notation works, is you have to cover every single separate interval. And in this problem, I had 3 separate intervals. I had that interval, I had this interval, and then I had this interval. Okay. So whenever you see a quadratic in the denominator, know that you're going to have to factor that to find out what x can't be. Because just looking at this, I can't really tell you what x can't be. The only way I can figure that out is to factor it and then solve it. Now, notice that the numerator is a cubic. Is there anything the numerator can't be?
No. Yes. No.
Actually, no is correct. The numerator can be anything you want. There is no value of x that makes the numerator difficult. We don't care if the numerator is 0. The numerator can certainly go from negative infinity to positive infinity. So there's much less restrictions on numerators. So I don't really care. Once I've figured out that x can't be negative 3 or positive 2, then the numerator, we haven't talked about the range yet on this. Let's not skip this problem quite yet.
All right.
Because the range is not so trivial. We know that the denominator factors into x plus 3 times x minus 2. Does the numerator factor into anything?
Well, I lost you for a second there.
Yeah, the numerator actually factors into something. The numerator is the difference of cubes. So the numerator is going to factor into x minus 2 times x squared plus 2x plus 4. Multiply those two together and you get x cubed minus 8. And I'm dividing by x plus 3 multiplied by x minus 2. Now, notice what happens here. Something very special happens here. We said x could not be minus 3 or 2 because it makes the denominator 0. But once we've factored both the numerator and the denominator, this x minus 2 cancels with that x minus 2. But, and here's the key but, it doesn't change the restrictions on the domain. I still have to carry forth the fact that x cannot be negative 3 or 2, even though I'm now looking at something that looks like this. I still cannot let x be equal to 2 because I have to abide by the domain restrictions of the original function And just because I was able to cancel out the numerator of the x minus 2 doesn't mean I can ignore that restriction. So in terms of the range, if we talk about this, we'll be talking about this problem for the next 15 minutes. I'm suggesting that we probably shouldn't do that.
Yeah.
Because it involves...
We can come back to it in a minute.
Well, it involves dividing this into that and changing it, and that involves long division of a trinomial by a binomial. We could spend a lot of time on it, but I don't think it's in your best interest. Let's go on.
No.
And if we have time, we can come back to it.
Okay.
All right, let's go to the logarithms part.
Let's see. I
Which one?
Went through and did those today.
Okay. Where do you want to start?
I did have a question about 96. I don't know if you can see that on there, but 96 on that picture.
Why don't you read it to me? I can't see it.
It says assume that f of x equals 2x squared plus 5, and that g of x equals negative 2x minus 3. And then the question says find f of x plus g of x. And with that place, I would just take the two equations of f of x and plug it into where that is, and then put the other equation under g of x and put it there.
Well, if they want you to add these, you just add them. No difficulty at all. I got a plus 2x squared. I got a minus 2x. I got a plus 5 and a minus 3. That's what the sum of them is.
Oh, okay.
Okay? In other words, I can't add an x squared to an x, so they have to be separate terms in the final answer.
Right.
If they want you to subtract them, same thing. No more difficult. The part that you're curious, that you want to know the answer to, is what the heck does this mean? Or
well, that is just, you figure that out and then plug it in.
Or fog. It could be called fog also.
Okay.
The way you do this is exactly as you said. You plug in g of x, this function right here, for there. In other words, what they're really saying when they ask you that, what would f of 3 be? How do you figure out f of 3?
You put 3 in place of all the x, so it'd be 2 times 3 squared plus 5.
Right. That's all I need. What would f of x cubed be?
You put x cubed in each of the x's.
Okay, which not in each of them, in this one. In other words, the f function only, not the g function. Okay, if I say what is f of x cubed, I'm going to put that x cubed wherever I see x, just like you said.
Right.
Still have to square it and add 5, but that would be what it would be equal to. And of course, that's equal to 2x to the 6th plus 5. So the idea here is that whatever I put inside the parentheses, you plug in for x, no matter what it is. So when I say f of g of x, what I'm really saying is f of minus 2x minus 3. And then how do you do this? Say again?
You put the negative 2x minus 3 in each of the places of x.
And there's only one place right there.
Right. Right.
Okay. You don't put it in down here because it's f of g of x. Now, if I said, what is g of f of x, what is that going to be? Is this stuff you have to know? It is, isn't it?
Yeah.
Okay. So how would you do
I'm just making sure I know this.
Yeah. So what is g of f of x?
You would put f of x in each place of x in the g.
Okay, so it would be minus 2 times 2x squared plus 5 minus 3, like that.
3.
So that's the way you do. Those are called composite functions. The Goff and Fogg, which are f of g of x and g of f of x. Okay, let's continue with, yeah, you were reading a problem? Oh, it was that problem. Did we answer that problem fully? 96?
Yeah. Yeah.
Okay. What else you got?
That's all the problems I have. That's all the questions I have for now.
Okay, because we got 10 minutes. You understand all of these that we didn't go through? You know how to do all of them?
Yeah, the 70 through 93. Yeah, I did them earlier.
Okay. Okay.
I had to call my friend for help on a few of them, but I figured it out.
Okay.
So, yeah. So
what's 86? Let's see if you remember.
I don't have the paper with me, but
well, that's good. That's why I'm asking, because you're taking a test tomorrow. You won't have that paper with you when you take that test either. So how do you do this problem? Do one variable at a time. What's the square root of 25?
5. So it'd be 5.
What's the square root of a to the 4th?
4.
It's a squared.
A squared.
Sure. A squared times a squared equals a to the 4th. Therefore, the square root of a to the 4th has to be a squared. What is the square root of b to the 7th? Take out as many, take the highest even number you can find in the exponent, which is 6.
Right.
Divide it in half. In other words, I can take at least that out. But that doesn't take care of everything, because what b to the square root of b to the 7th really is it's the square root of b to the 6th times the square root of b. If I take the square root of b to the 6th times the square root of b, I get the square root of b to the 7th. So the thing is that we know that that is precisely b to the 3rd. So the answer is b to the 3rd times the square root of b. So that's what I want to put right there. B to the 3rd times the square root of b. And the last variable there is the square root of c, so we can't do anything with that. That remains under the square root symbol. So that's how you do that problem. Tell me what the square root of y to the 9th is.
Hello?
Yeah, I don't know if you heard me. Can you tell me what the square root of y to the 9th is?
Y to the 3rd?
No. Do the same thing I did with the b. Break it up into an even number. In other words, let's make it the same as y to the 8th times y to the 1th, which I can separate now into two things, y to the 8th times y. And now I can pull out what from that? What's the square root of y to the 8th?
Y to the 4th.
Okay. So y to the 9th is y to the 4th times the square root of y.
Right.
Okay.
All right, well, cool. All right, yeah, like I said, I'm planning on signing up for another session like Tuesday night or Tuesday afternoon because I have
Tuesday.
4 o'clock off.
I don't have a lot of times available on Tuesday. Let's go look right now, just so you know. Let me pull it up real quick here.
Okay.
My Tuesday is very full, and then Wednesday is empty, as you can imagine.
Yeah.
Everybody has their finals next week. I got any time after 7, but that may go quickly. So if you want one of those times, we should do it now.
Okay.
Which one do you want, 7 or 8?
We'll do 7.
Okay.
Actually, let's do 8 o'clock because I have something going on at 5, and I don't know how late that's going to go. So we'll do 8 o'clock.
You got it. Much easier for me to put it in than you, huh?
Yeah.
I don't know how. You have to type in your name and email every time you do it?
Yep.
Wow. It doesn't memorize it?
Nope.
Wow. That's too bad. I didn't realize it was that way. Okay. I will talk to you. I will email you that meeting ID at 8 o'clock Tuesday night.
All right, Tuesday night. I will see you then.
I guess you probably need to send me some more problems, or else we can go over problems that we haven't gone over yet.
Yeah, I'll do that on Tuesday night, like just before.
Okay. Talk to you Tuesday,
All right,
Joel.
cool.
Bye-bye.
All right, bye.